Okay, so this is the particular solution. If you actually get the second derivative, you get this expression, and you need to substitute into this equation. Okay, so if you actually do that, you are going to have mx cos omega t plus your k, so you can actually see that all these expressions have this cos omega t, which you can actually cancel it out, and you can just rearrange that. Then you will just have your x, so you have k minus m omega square everything, x equals to f naught. So if you want to solve for your x, is equals to f naught divided by k minus m omega square. Okay, so you have basically this is the expressions that you can use to actually solve for your x. Okay, so that is how you get this equation. From there you can actually, if you have f naught, k, m and omega, you can solve for your amplitude. So the total solution just now, if you substitute, this is actually your x, and you can see that this part here is your xh, and this part here is your xp or x steady state. Okay, that is how you get the total solution. Alright, using initial conditions, because you can see here, you can also solve for your A1 and A2. So using your initial conditions, x naught and x dot naught, you can also find your A1 and also A2. So you can substitute back into the formula for A1 and A2. So this is actually part of your homogeneous solution, and this is your particular solution or steady state solution. So from there you can also see, if you actually plot these two graphs, this is how it looks like, where when your omega over omega n is less than 1, okay, you can see that there is a period of 2 pi over omega here. Okay, as you can see, the difference between when your omega 1 less than 1 and greater than 1. Alright, so that is how it looks like basically. Okay, the inner part, which is 2 pi over omega n, you can see here these waves actually moves at smaller intervals than the second one, yeah, when omega over omega n greater than 1. Okay, the maximum amplitude can also be expressed as this capital X, where f naught over k has a physical significance, where it is actually the static deflection. So this is what we call static deflection of the spring under a constant load of f naught. How do we get this equation? If you remember from this one, okay, what you do basically, you just divide it with k. So that's how you get for both. Okay, so that's how you get f naught over k, and also you have your k divided by k is 1 minus, so m divided by k is omega n square. Alright, so that is how you get this equation. So this is actually static deflection, F naught over K. Or maybe if you cannot remember that, perhaps you can also remember that F naught is equals to K times static deflection. So this is like Kx, which is the deflection of the spring once you applied this F naught or input to the system. So the previous equation can also be expressed in terms of this, where if you can see, the difference is you bring the static deflection to the other side of equation, so that's why you have left with 1. Okay. So this is another parameter that we call dynamic, the ratio of the dynamic of the static amplitude of motion. Sometimes we call it magnification factor, amplification factor, or amplitude ratio. So make sure you know what it means by that. So take note of this equation. So this is when you actually draw the figure of this magnification factor versus the frequency ratio. So these are the common terms that we use in vibration. Omega over omega n is frequency ratio. Sometimes we also use a lot as R. So you can see here, so your R is equals to omega over omega n. So this is in a case where you can plot plus minus. If you actually plot it in terms of amplitude or absolute number, okay, you can also see that the graph, the negative graph, will actually goes up, something like this. And this is the infinity point where it's actually R equals to 1. Okay, what does it mean by that? If you look back to this equation, when you have, maybe this equation is better. When you have R equals to 1, so you're going to get 1 minus 1, which is equals to 0, isn't it? Okay, at R equals to 1, or your omega equals to omega n, or at resonance, in other words. So that's why it goes to infinity. So that is why in this case at R equals to 1, your amplitude ratio or your magnitude basically, it goes to infinity. So what happens in other cases when your R is between 0 to 1 and when your R is greater than 1? So in terms of phase, the response of a system is in phase with the excitation force, but if it's greater than 1, the response is 180 degrees out of phase. So in terms of the response, when the R approaches infinity, the vibration response approaches 0. And when R equals to 1, it becomes infinity. As I said, it is at resonance. So at resonance, vibration response increase linearly with time. So this is the conditions, and a lot of times you would want to avoid, when we say at resonance. So when we say the system of resonance, again, omega equals to omega n. So you can see the solution, the general solution is given as this, where your F naught equals to F naught over m. So at initial displacement, x naught and v naught, or x dot naught, you can see that this is actually your xt. Okay, after you substitute your x naught and v naught using the equation that we had in the previous slide. So this is how it looks like when it is resonance. If you plot the displacement versus time, So it goes, it's getting larger as it goes over time, and the amplitude of vibration becomes unbounded at omega equals to omega n. Okay, the last definition that we want to know or understand is what we call the beat phenomena. A very important phenomena occur when driving frequency becomes close. Okay, so this one is slightly different. It's not exactly, but it's close to it. So this is what we call beat. In this kind of vibration, the amplitude builds up and then diminishes in regular pattern. So beat phenomena, as you can see, it has a slightly different response given by this equation. And you can also note that you can find at what frequency it occurs because of this relationship. And if you substitute, then you have the general solution, okay, as given as such. So if epsilon is small, the function sine epsilon t varies slowly. So its period equal to 2 pi over epsilon is large. Okay, so the above equation, therefore, okay, which is this equation, represents a vibration response with a period of 2 pi over omega and of variable amplitude equal to this expression, so which is this amplitude. So that's what it says because it has double sign there. From this, okay, you can also get the period of the beat, okay, where it is actually 2 pi divided by the difference of this omega n and omega. So this is how it looks like, what it means by the beat phenomena. You remember we have a similar graph, but now if the beat phenomena occurs, you can see there's this kind of like envelope here that shows there's a beat there due to this. So this is the amplitude and this is the frequency of the overall frequency, and also the smaller frequency of each of the wave, because there are two parts of it, yeah, two sine functions. Alright, so we've done with the lecture. Let us take a look at example. There are two examples related to this lecture. So in this example 1, you can see that I've put the variables related to it. 4000 Newton meter subjected to force, 100 Newton is F naught, frequency 5 Hz is F. So don't forget your F, you have to actually times it with 2 pi to get your omega. So that will be here, 10 pi. And then your F naught is here. So 100 sine 10 pi t will be your F naught sine omega t. So that's the input to the system. The amplitude of the force motion of the mass is observed to be 20 mm is your capital X. So don't forget to put everything in terms of, so omega is in radian per second. Okay, and then you have your capital X should be 20 times 10 to the minus 3 meter. So meter is the standard unit for that, and what you want to find is you want to find m. So in this example, we have to find m given other parameters. You have f naught, you have k, you have omega, you have x. So you have m. So easy peasy. So first thing, convert the in terms of radian, 10 pi f, and then you also have the static deflection f naught over k. From there you have either you use this equation, or you can also use equation relationship between your x and your f naught. k minus m omega square. You can also use this one because you have everything. You have f naught, you have x, you have k, you have m. So you can also solve for your omega. Okay. Sorry, you have omega. Okay, you have omega, but you do not have m. So you can also solve for your m, or you can use this formula. So there are two ways of doing it. So if you use this formula, then you have to take the ratio of the natural frequency. You solve for your r, or what we call r. After you get your r, you can get or solve for your omega n, and from there you can get your m. So either you use this equation or you use this equation, you should get the same answer of 9.1 kilogram. The second example is very easy. You just want to find the period of beating. Okay. Given these two frequencies. Yeah. So this one is easy. It's very straightforward equation that is given in your slides. It's actually slide 21. So this equation is from, you can refer to slide 21. So you just substitute. So basically make sure you convert your f is in hertz in terms of omega. So you just times 2 pi. Then you should get 5 seconds. So very easy. So make sure you look at the tutorial questions in order to further understand this lecture. Thank you.